A very warm welcome from our side here from Schlotau and Bauer to a new webcast. We are really happy that you joined us today.
So today's webcast, Model Predictive Adaptive Control with ImFlow. So not only would you have noticed that there is another adaptive control or network control webcast this week. So it seems that now we have two adaptive controls. So this is exactly the reason, or this is one of the topics of our webcast today. How do ImFlow and former Ines, now MyCityAdaptive, work together or not maybe work together? How do they occupy different places in the Swarco and Schlotau and Bauer portfolio? What is the difference? Where do they share certain situations where it might be viable to use them, or where do we have a clear-cut case? Okay, that is a case for ImFlow, that is a case for Ines or MyCityAdaptive, better so to say. Who am I? My name is Torben Titze. I have been working for Schlotau since 2008. I was the product manager during many years of Ines, which is now MyCityAdaptive, and I was also working as a trainer for our Lisa customers, training them in the use of Lisa. And as you can see, so you might know me, or you've probably known me from other webcasts, which mostly have been about Ines and MyCityAdaptive or about Lisa. So I am probably one of the best persons to talk about the differences to MyCityAdaptive and maybe a bit of a background. So where does ImFlow come from? ImFlow was developed at Peak or Peak Dunic, a company that is part of the Swarco family since, I'm not sure, 2018 or 2020, something around that. Maybe 2020. So it has become part of the portfolio, and also for us at Schlotau and Bauer, it was important to learn how it works, what are its strengths, how to use it, because we are also now responsible for doing projects with it for the marketing side. So we want to share these learnings that we had during the last 2 years. So content-wise, we're going to start with a little introduction. What is ImFlow? Then touch this part. Where are the differences between ImFlow and MyCityAdaptive? Why does it make sense to keep both products in our portfolio? So it's not the idea that ImFlow should replace MyCityAdaptive or MyCityAdaptive should replace ImFlow. Rather that they both cover different fields or different situations. Then we're going to talk about the ImFlow traffic model a bit more in detail. We're going to talk about the tools that ImFlow consists of. A few questions about what detection do I need to do ImFlow, what situations or what requirements are there detection-wise, then generally technical requirements, and we're going to show a few reference projects with ImFlow. So what is ImFlow? We described it here as a model predictive, or you might also say model-based adaptive control. ImFlow is optimizing traffic in real time. So it is having several layers or several optimizers that are assessing the current situation and making decisions on a second-to-second basis, or even every tenth of a second when we talk about the Netherlands or controllers that work in such a cycle. It has a flexible scope, so it can run networks just as good as individual intersections. So ImFlow also includes or is a control algorithm that is not only working at the network level, as for example MyCityAdaptive does, but it's also controlling individual signals on individual intersections. You can run it either in different modes, the most extremes being a fully adaptive mode or simply a traffic actuated mode, depending on the detectors that you have at hand and on the goals that you want to achieve. A big difference also to MyCityAdaptive, it's independent of a traffic central. So we will see that ImFlow can be run on all kinds of devices and in all kinds of environments. So it can be run on a compatible controller, or it can be run on a server, or it can be run in the cloud. Doesn't really matter on which hardware the algorithm is running and executed. More important, what data is available, so to say. And last point, with ImFlow is CCAM integrated, we see that the algorithm that we're using, or that ImFlow is using, is mostly based on waiting times and on the simulation of individual vehicles. So the additional information that we're getting with CCAM is very easy to integrate into the control algorithms, because it's basically providing information that we're simulating otherwise anyway. So, but more on that later. In general, how is the algorithm structured? As I said, there are several or two optimizers working hand in hand. They are at the core, there's the optimization, taking into account the traffic state that is based on the measurements that we're making. And this results in some kind of actuation. And the main way of influencing these optimizers is through either policies or through constraints. Policies, you might also call them parameters, which influence the optimization. And then we have constraints, which are more like safety times, intergreen times, and so on, or offsets. But we will look at that in detail later on. In general, what you can also take away from the slide, evaluation is always based on a cost function. And this cost function, we will see, is cost in this function is waiting time. So any cost in ImFlow is always calculated that way, as we will see. To look at the differences one more time at a glance between ImFlow and MyCityAdaptive. First of all, ImFlow, independent of a traffic central, can be run on a local controller or on several local controllers or in the cloud or whatever, whereas MyCityAdaptive or Ines always is either integrated into a central in the case of MyCity, or if you should use a third-party central interfacing with the central, so we need an OCIT-based infrastructure, an OCIT-based environment where controllers are getting commands that way, or if it's not OCIT-based, at least it needs to run or in a similar data model where we have the choice between different programs. In ImFlow, you basically don't have different programs. In ImFlow, the cycle time is updated and calculated in the algorithm. So we're not looking at different programs. We're more looking at a control that is adapting every cycle to the given situation. So we have dynamic stages and we have dynamic stage lengths, whereas as in MyCityAdaptive, the stages are fixed, or the stage order is determined by the local control, wherein here ImFlow also is the local control. So dynamic stages are also coming from that side. Also, we have dynamic offsets, similar to MyCityAdaptive. Not also one point that is different to MyCityAdaptive. We have the full public transport and CCAM integration, so the algorithm can directly consider the situation for the public transport and so on. Whereas this in MyCityAdaptive is totally dependent on the local control. One thing that you cannot do with ImFlow that you can do with MyCityAdaptive is using your existing infrastructure. So MyCityAdaptive is based on the idea that we don't really care what is going on in the local controller. It can be a fixed time, it can be traffic actuated, it can be any kind of control method that is based on different parameter sets. So there is that yield, which would be kind of exclusively on the MyCityAdaptive side. To talk about the traffic model that is used in ImFlow, maybe the first thing that one should understand or that we should talk about are the two levels of optimization. And to talk about those, we have to talk about the stage definition in ImFlow. So the two optimization levels are, first of all, the network optimizer. The network optimizer is determining the stage sequence and the stage duration. So it is calculating for the planning horizon of one cycle, what stages should be used in the upcoming cycle and in which order and in which length. And then on the second level, the intersection optimizer is determining what primary and alternate signals should be activated, meaning that the current stage, the length of the current stage or the length of the signals in the current stage is determined by that intersection optimization. So what is the stage then? So we're looking at the stage definition down here where we have different colors for different arrows, and this is not just by coincidence. In ImFlow, these colors actually have a meaning. For example, if you look at this stage 1 and we have this right turning signal, and at the same time we have a parallel pedestrian, if this is an actual right turning signal, we probably would not be able to have green time for them at the same time. The same goes with here, this left turners and the right turners, and these left turners, they could not go at the same time. So the difference here is between primary and alternate signals. These primary signals that we see here, the green ones, these are basically the same like in the stage definition that you will find in LISA. So in LISA, stages are always fixed. You see that the signals which I have in phase 1 or in stage 1 are these three, and here in ImFlow it would look like this to have a similar definition. All the signals here are green, so they are all primary signals, and that means when stage 1 is active, these signals will be activated at the beginning and also be held for as long as necessary. When we look at the additional definitions that we have seen, these blue arrows, then we see this is not the same anymore as these 3 stages as we would define them in Lisa, because these blue signals, they would only be activated if the intersection optimizer finds that the primary signals that are conflictive with those would have ended before. And so to have something similar to this in Lisa, we would have to change this pattern a bit. So what is 3 stages in ImFlow in the Lisa world would actually be 1, 2, 3, 4, 5, 6 stages being comprised of primary and secondary signals. So you see you have more flexibility in an ImFlow stage than in the Lisa stage. This means there is more to find in this diagram than in a traditional one. Now that we understand how these stages work, let's take another look or understand one more time what do the network optimizers, intersection optimizers do. So the network optimizers is deciding the stage sequence, as we said, intersection optimizers deciding the signals in between. And then there's the third control level, optimizer, network optimizer, intersection optimizer, and controller. The controller itself basically is just there to monitor minimum and intergreen times, so make sure that the safety measures are in place. So how does the network optimizer actually decide between these 2 stage sequences? As I said, it's assessing them based on the total waiting time that the optimizer expects them to produce. And to get to these costs, to get to these total waiting times, of course, we need a simulation model. And without going too much into detail, what is actually happening in the background is that the whole network of intersections that is controlled with ImFlow at a time is actually being simulated. We have actual vehicles that are simulated with a certain speed. We know when they're in a queue waiting at a stop line. We know where the last vehicle is stopping. That's the so-called the horizontal queue. So vertical queue means the total number of cars between stop line and end, and then we have the horizontal queue, meaning the distance to the last car that is stopped. And the waiting time or the cost function then encompasses, first of all, a delay cost function, meaning we are comparing the time it actually takes for a car to pass a link or to pass a certain part of the road, and compare this with the free speed that it would have taken. And then we also add a certain stop cost. So whenever a car is stopped or a vehicle is stopped, this also leads to certain cost that does not only represent the time that you're stopping and the time that you need, but also reflects the cost for the acceleration and braking, the energy loss that is produced by that. With this cost function, you can actually balance your control with these costs. You need one more thing as a parameter, and these are the entry and exit costs. And then there are several other costs, but these are the most important ones. These are actually factors that you can put on certain parts of the road where you can weight different or be weighing different the entry or the exit of an intersection against one another. If you are weighing the entry cost higher than the exit cost, then you will do everything possible that there is no delay in the entry to an intersection. If you weigh the exit cost higher than the entry cost, then you might stop vehicles at the entry to a network because you don't want them to be delayed later on at the next intersection. This is the part that might be reflected in policies, the cost function and the cost factors, which can determine which flows, which modes, and which directions inside your network are being prioritized. And on the other hand, we have constraints. So everything in the cost world is always balanced against one another. When you're putting certain costs on, let's say, the delay of a bus, then the function will try to give the bus as much priority as possible until the cost that it would otherwise produce is kind of equalized. But this is always something that, it's a question of prioritizing certain flows, and it might be hard to predict from the outside how much priority a bus really gets in the end, because there is still some leeway or some other costs being involved. The other side, when you say, okay, but there are certain parts in my control that I need to make sure that they work, this is the so-called constraints. Constraints are setting boundaries for your control and saying, okay, there are certain stage sequences that I cannot allow, or there is a certain green time that I have to make sure that a certain direction always gets, or I have to make sure that there is a certain offset between two signals. And all this is subsumized under the this headline constraints, and we have 3 different types of constraints for 3 different levels of control. For the adaptive optimizer, we have adaptive constraints, meaning we allow or disallow or prioritize certain stage sequences, and we also give certain green time parameters, saying, okay, a certain stage needs a minimum green time of X seconds, or a certain movement has a dynamic part of Y seconds, and so on. Then there are functional constraints for the intersection optimizer. This is stuff like pre-starts, early cutoffs. We will see that in detail on another slide later on. And the security constraints or safety constraints, which are implemented in the controller. That is something that's probably very universal, not only for ImFlow, into green times and minimum green times. Of course, something that is always monitored and made sure that it's taken into account. So adaptive constraints, as you can see, now we also have colors for the certain stage transitions here. So green would be the standard stage transition from a certain stage. Blue would be something like an alternate. If there is a demand for this stage, we would go the blue way. Otherwise, we could go back to the other stage right away, stuff like that. Functional constraints, these are all a few examples, like a common start for certain signals, or a pre-start for one signal over the other, so certain offset, early cutoff, inner and outer crossing. All this is subsumized under functional constraints. I don't have an example for the minimum green times and intergreen times because I think it should be clear what's meant with that. When you've defined all these constraints and parameters, especially for the green times, you might be interested in, okay, what is the result? What will the control do with that under certain circumstances? And ImFlow has the possibility to kind of look at these resulting plans in its configurator. For example, this plan would represent what happens if all directions send a demand and have a maximum demand on them. Which tools do we have in ImFlow for the realization of a control? First of all, to do the basic configuration for an ImFlow control, we can either use Lisa for the basic data, introducing signal groups and some basic geometry. Then first or second step is usually creating a simulation network in Vissim. Based on this Vissim network, we can import this to ImFlow, and in ImFlow we do the definitions of the elements that actually comprise the ImFlow control, so intersections, road links, and routes, and so on. So these layers and objects on the base layer, this information can be introduced in either in Vissim or in the ImFlow editor. But these ImFlow model information, this has to be done in the ImFlow configurator then. Once we have a controller, we can simulate, or we have done all our definitions, or we can simulate this in Vissim and monitor this control, or the monitoring tools. It doesn't really matter if it's a Vissim simulation or if it's outside on the street. So here you see this time horizons, this vertical line representing the current second. You can see the stages that the network optimizer has chosen up until now and that it is predicting or recommending for the future. You can see the current signal times and the signal times for the next 60 seconds here. Also, we see the vertical queues of certain signals represented here. So all the signal groups, all the detectors are being traced and can be monitored like that. At the same time, we can produce certain KPIs and certain statistics per signal group, current volume, delay, stops, queue, and so on. And this can be monitored in real time. Where does Lisa come into play in this whole thing? So we have Lisa as a basic configuration tool where we can design the intersection. This planning can then be taken over to either to Vissim or directly to ImFlow. So we can do some basic configuration of the signals and stuff like that, but still the main part will be done in ImFlow. But if you have some existing basic data, this could also be a starting point for your ImFlow configurations. When you are talking about control algorithms and different approaches, one of the first questions is always, so what kind of detection do I need for this control mechanism? Will it fit with my existing infrastructure? What is actually needed? What could be a minimal configuration? What is a maximum configuration? What is ideal in my situation? And the answer is just as broad as that. It kind of depends on what you're trying to do and what you have. So let's see, if we look at this configuration here, you might be in shock having 4 different detectors in this configuration, close to the stop line at 35 meters, at 100 meters, and at the entry of a link entry detectors. This is something of a maximum configuration where you have link entry detectors, you have stop line detectors at the next intersection or at the actual intersection, and you have gap out detectors here, which are kind of optional in any way when you have also an actuated mode that you want to have active at certain times or combine with the Q model or the adaptive mode. If we look at different modes, so these gap detectors at 35 meters, they are really just for the actuated only mode. So when ImFlow is not using its adaptive algorithms, but only is used to determine the stage length of a given stage sequence, which is something where you don't really need ImFlow for that. So it is just a way that ImFlow can be used or that it can still operate on. It kind of mimics your usual gapping out standard sequence control, but maybe would be a waste of an ImFlow license to actually do it like this. Then we have kind of I would say the optimal way or the optimal configuration in which ImFlow can operate, meaning that we have stop line detectors to make sure that we also count the number of vehicles at the stop line in the moment that they are leaving the link. Then we have these mid-block detectors at somewhere at the 100-meter mark. These are really just to measure the current flow inside the road link, and we have link entry detectors where we count what is going into the road link. So stop line and link entry, they should be, the main requirement for them is to be counting reliably. The mid blocks are actually there to determine traffic flow. So these could be speed detectors. This could be loops with a certain length to determine the speed. With occupation, it doesn't really matter. If you don't have the mid blocks, just as well. So this still works fine for the adaptive mode. And to look at the minimal configuration for ImFlow Adaptive, the minimal requirement is that you have link entry detectors. And if we say you have to have link entry detectors, depending on the situation, when you compare these two configurations of this intersection, you will see that you could probably define these link entry detectors as virtual detectors that are somehow comprised of the flows that we measure on the stop line detector. So when we say it has to look like that, it has to be, these measurements have to be reliably calculable. So you have to reliably be able to calculate them. And here in this case, that might even be possible with just the stop line detectors. But the link entry detectors are mainly important because of their calculating the vectors or the expected arrival vector on this link. When we go back here to this one, delay and stop cost function, it's kind of relying on to know whether or not a car has to stop on the way to the stopping line, and to estimate if there are cars inside the link. This information has to be there and has to come from somewhere. So just having stop line and not link entry is probably not optimal. So that's why these are the most important ones. So this was the requirement on the detection side. Then we have some general technical requirements when we look at how ImFlow can be deployed or installed. It can run, as I said in the beginning, in the cloud. It can run on the Traffic Central. It can run on an RSU or some outstation that can run the code. It could be running directly on the CPU of the TLC, or it could run on an extra CPU that you put in the cabinet. We will see that now in the example of it running with an Actros controller. In general, what we need is an IP-based private network. So the controllers have to be able to talk to one another directly over TCP/IP. or the different instances of ImFlow. We need link entry detectors, as I said, for the queue model to work. The traffic light controller should be TLCFI enabled, so the actual states of the signal heads are being triggered over this TLCFI. And we need RISC-FI enabled RISC for CAM, SRM, and SPAD data. In the case of the Actros, how does that work? In the Actros controller, the Actros controller is actually running a Lisa logic, an OMTC style control, and this control then hands over or activates what is called a TLCFI extension. So technically, and the Actros is running a Lisa control. You can even have a Lisa control and Lisa-based fixed time programs in your planning, and then you have a certain plan that is kind of marked as a TLCFI program, and then this will start the TLCFI extension, and then the controller will be waiting for commands from the TLCFI proxy. What the controller does in this configuration, it's basically doing the safety part, minimum green times, inter green times, and stuff like that, and the rest is handled via this interface. In that case, also you can run ImFlow in the cabinet on an additional CPU in a small box, or you can run it somewhere on a server in the private network. The technical requirement for this is that the firmware of the Actros is G5 TC6 or higher. And the control should be exported with Lisa version 8.03 or higher. Very technical stuff. Let's look at something more practical and more tangible. We're already reaching the end of my presentation. So I have compiled some references. These are not all the references of cities running, of course, not all the cities that run ImFlow, just a few examples that I picked Helmond because this is one of the longest running implementations. So since the year 2012, you can see here the main arteries, the main network in Helmond is run with ImFlow successfully. Then we have another example, Almaty. It's city in Kazakhstan, if I'm not mistaken, where we're running 200 intersections with ImFlow in adaptive mode, and you can see that the improvements in certain KPIs are really, really very impressive, I have to say. I mean, of course, this probably comes from a comparison with fixed time, old controls, so on. But even having that in mind, this is really on the upper end of what I think is achievable under any circumstances. So 33% inflow improvement, 37% less stops, 27% lower emissions, less fuel consumption, travel time decrease of 30%. That is really a very, very, very good number. Also, something that you can do with ImFlow to have GLOSA-enabled corridors, speed recommendation coming out of ImFlow. All these interfacing or all these services that interface with other systems that are relying on a very good awareness of the situation and of very detailed data. ImFlow is pretty much perfect for that because it has a detailed simulation model and its own algorithms are basically based on that. We have a very good understanding of the current situation, so it works pretty well with that. Same is true for CCAM integration, CCAM messages, information about individual vehicles coming at certain speeds towards the stop line. This information, usually when you don't have CCAM, you're having a detector and what ImFlow does as soon as it is counting a vehicle, it is creating a digital representation of that vehicle and simulating it and tracking its position. This part of creating the vehicle, you can actually take that out because you have the message and you have the vehicle and you have updated data about it. So the more CCAM information, the better the algorithm, and there is no need to kind of change how ImFlow works on its basic level. You just can feed it with better information. So we are currently looking for pilot projects in Germany. We're also looking for customers outside of Germany. So inside of Germany, we are still on the pilot phase to get everything working together with the Actros controller. Internationally, the implementation with ITC is there, and it's a finished product, and it's ready for us to be ready to be distributed. So if you have any questions, anything in mind, any city in mind, please contact us via ImFlow at Schlothauer. And if you have further technical questions, also relate them to us, and then we might relate them further. There is a question. Hello, Mr. Titze. Thank you very much for the interesting presentation. ImFlow, may I ask how the network optimization works when ImFlow is running only on the CPU of the TLC? Or did I get this wrong? Thanks again and all the best, Felix Robert. So it's running on the CPU of the TLC, and the TLCs are talking to one another. So every TLC is always getting the information of the neighboring intersection. So if we look at, so let's say, yeah, there's a better slide for this, but I don't have it here in my set right now. So you have to imagine that the information about the next 60 seconds, so the planning for the stages or the planning for the greens of the neighboring intersection, or the upstream signals and the downstream signals, are also part of the optimization at my intersection. Of course, there's a delay of 1 second, so every intersection knows what the neighboring intersection had as a result of its optimization the second before. So every intersection is optimizing for itself, and the result is sent to the neighboring intersections, and based on this, in the next second, they can do their estimation. You might argue that there is no network-wide optimization in that regard, because there is never the knowledge about the whole corridor, but corridors, on the other hand, are taken into account via prioritizing certain routes. So you know the neighboring intersection, and you also have the information if the neighboring intersection is on a priority route, and if I should prioritize the offset to that intersection. And as far as I know, this is also how Scoot does it. So other adaptive solutions like Scoots and Scats, as far as I know, they also never look any further than the next intersection. There is the idea of maybe putting in more information in the future coming from a corridor optimizer, but right now this is the way it works.
Thanks a lot for joining us today. And as always, we are at your service if you have further questions. Please contact us at service@schlothauer.de if you have any technical questions, or if you want a quote, an offer, have any sales-related questions, then please contact us at lisa@schlothauer.de. Thanks and have a nice day.